Hi, I'm Olivia, everyone's favorite math teacher, and in this video we're going to look at exactly what the relationship is between a function and its derivative. The advantage of being able to examine a derivative as a function and as a graph is that it turns out that the two of them are linked in a very interesting way. If you remember, the entire point of the derivative is that every point on this graph is every point here the rate of change, meaning that the direction of the slope of every point on this graph is reflected by the position of that point on this graph. So if I have a positive slope here, then I will have a positive point on this graph. If I have a negative slope here, I'll have a negative point on this graph. And if I have a zero slope here, so a horizontal line, I'll have a 0 point on this graph. So it's where I'm going to transition from positive to negative. But another thing to think about is that we have something called inflection points, which is where our slope is going from the rate being basically speeding up the rate of decrease. And on our graph, this is where we would see a positive, a minimum or a maximum. Okay, basically kind of think of it like a vertex in a parabola. And in examining the derivative, we can find those places on our original function. So going back and forth between these, we can find very useful and very valuable information. And what's even more important and more interesting is that just like we can go an original function and go to a derivative and find valuable information, we can take a derivative and get a second derivative and find information about this graph. And then from a second derivative, go to a third derivative. And for marking purposes, if we're using the Lagrange notation, we would simply go, our original has no hash marks. First derivative gets 1 hash mark. Second derivative, we put 2 hash marks. Third derivative, we would put 3. Fourth derivative, we would put 4. I've never really seen it go beyond a fourth derivative using Lagrange notation. And then when we're talking about using the Leibniz notation, you would go d dx. And then it gets a little bit weird because what you do is you put your hash mark on the top and then you put your other hash mark on the x. And so you actually kind of alternate them. It's interesting, and you'll see that more when you start working with multivariable calculus because it gets a little tricky with where you position the markings. One of the other interesting things that we need to talk about is going to be differentiability, which has a lot of similarities and ties to continuity, but we're going to look at that next. Now, if you recall, the definition of continuous is that the limit at a point has to be equal to the value of the function at that point. And then for the function to be continuous on an interval, it has to be continuous at every point on that interval. The definition for differentiable of a function is very similar, but instead of looking at the function, we look at the derivative of the function. And basically what we say is the function is differentiable if the derivative exists at that point, and then of course it's differentiable on the interval if it exists at every point on that interval. And we are saying on the open interval, okay? Because if we're talking about a closed interval, we would just go, well, the open interval, a step out from it. Now, these are the 3 common examples of what causes a function to not be differentiable at a point. The 2 that are the most easy to see are of course going to be a discontinuity because, yeah, obviously it's not differentiable here because remember, when we are taking a derivative, that's a limit. And for the limit to exist, it has to exist from the left and the right. That's built into the definition of a limit. And we know that a function with a discontinuity, the limit does not exist from the left and the right. The limit exists from the left, the limit exists from the right, but it's not the same limit, so therefore the limit doesn't exist here. This is not continuous. This point, it's not differentiable at this point, right? It's differentiable here, it's differentiable here, but not exactly at this point, okay? Now here, this fails for a different reason. And it fails because the other thing about the derivative is it's the slope. This is a vertical slope. And this kind of is one of those things where, yeah, we're in calculus, but you go all the way back to, like, I don't know, what, 7th grade when you learned what a slope was? And we all learned, hey, rise over run. Oh, wait a second, a vertical slope has no run. A vertical slope, oh, it's a 0. And remember, we take the limit as h approaches 0, but the x at that point is still 0 because we're not talking about the original function anymore. We're talking about the f. And so the x in the derivative would still be 0 at this point. So therefore, at this point only, the derivative doesn't exist because we end up having a vertical slope. Okay? We'll look at an example of that in just a moment where it happens. And you usually get something like an asymptote or some other interesting phenomenon in the derivative. Now, this version, it's a little trickier to see, and in order to understand this, you do need to go back to your definition and actually work it through. This is the absolute value graph. And absolute value is differentiable here, and it's differentiable here, but it's not differentiable at this corner point, okay? And the reason it's not differentiable here is because as you approach this, yes, absolute value is continuous, but as you approach that point, think about your absolute value graph. Well, your absolute value is a piecewise function, and as you come at it from one side, you're using the positive x, and as you come at it from the other side, you're using the negative x. So if we were to then take the derivative of this, well, the derivative of that would mean that, okay, well, we would have the positive and we would have the negative. So that means that the derivative would be, oh, wait, we have a positive slope and we have a negative slope. So the graph of that, just thinking with our graph knowledge, on one side, we're positive. On the other side, we're negative, and we never go flat. At no point do we curve over, become flat, and then switch. We just instantly are negative on one side, positive on the other side, and we smash into each other. There's no flat point. There's no point to shift over. We don't ever cross the x-axis, which means the derivative has a discontinuity. So the derivative fails the limit. So therefore, the derivative doesn't exist at that point exactly. Okay? And we'll also look at that one. This is two different ways for you to demonstrate to yourself that in fact that corner point on the absolute value causes it to be non-differentiable. So the first way is simply using the definition of the tangent line and the derivative being the slope. Because remember, if we're talking about the absolute value and we look at the piecewise definition of absolute value, when we're on the positive side, meaning our x is greater than or equal to 0, we have a slope of 1. And when we're on the negative side, we have a slope of -1. And both of those slopes are constant on both of those sides, meaning we have a constant flat slope of 1 on both of those sides, approaching this point. And then at that point, well, we're up here. So that means we have a slope of 1, so we have a constant line, a constant flat line of 1 coming to here with a closed circle indicating that we would be here on our graph. And then We have a negative 1, so we would be here with an open circle. But with the derivative, we're taking the limit. So the limit from the right would be positive 1. The limit from the left would be negative 1. Because the limit from the right and left do not approach the same value, the limit does not exist. So therefore, at this point, we're not differentiable. Now, if we go ahead and actually attempt to compute the limit, when we're computing absolute value, again, you need to reach back to remember that when we work with absolute value, we always have two equations. We have the plus version and we have the minus version. And with a limit, the way we know which version we're working with, whether we need the plus or the minus, is we go back to our piecewise function. And so because we're coming in from the right, we use the plus. When we're coming in from the left, we use the minus. That's what it tells us right here. Coming in from the left, we use the minus. So when we're taking the limit from the right, when we drop our absolute value, we use the plus. When we drop our absolute value from the left, we use the minus. That means from the right, we get exactly what we thought, a constant 1. And from the left, we get a constant negative 1. They don't approach the same value. Therefore, at that point, the limit doesn't exist. So therefore, we're not differentiable only at that point. So one of the problems, in fact, the only problem I'm going to give you, is a slightly difficult one, but it demonstrates the idea of the vertical slope in a problem. I am going to give you a hint with this one because it is difficult. So I would suggest, again, like on the last video, try it without looking up a solution if you can. But if you can't, don't hesitate to go look something up. Use your tools. Remember, this is all about learning. One thing I forgot to cover was the relationship between differentiability and continuity. Being differentiable infers continuity, but being continuous does not infer differentiability, as we demonstrated with the absolute value. The problem is having either a vertical slope or having a corner or a kink can kind of, well, not to put a pun on it, but put a kink in your plans. So you always need to make sure that you check. Sorry for those people that don't stick around to the outro. I'm sure this will get covered in your classes though. But aside from that, I do hope that this helped everybody with working with derivatives as functions. And as usual, if you have any questions, make sure to drop into the comments or join us on Discord. Have a wonderful day. And the solution to the one problem will be after the outro.